if someone were to ask me the simple question, can GT Suite model hydrogen and ammonia, my quick answer is yes. We can go into individual details, but that's the broad picture. And we're always trying to refine the model.
Hello everyone, good morning and welcome to our GT Tech Talk podcast. We are joined today by our hosts. I'm Abhishek.
And Divya.
And we have our guests here, Lalit and Jeremy. Today we are going to talk about net zero carbon fuels. Let's get started. Would you mind introducing yourselves? What's your background? How long have you been at GT and what your current work is?
Sure. So I'm Lalit Patidar and I'm a developer in the Reactive Flow Systems team, and I've been here in GT for 4 years, and I mainly work on combustion and emissions modeling and with our chemistry solver. So that's my background. I'll pass it to Jeremy.
My full name is Thomas Jeremy Wanat. I often go by Tom with customers, but go as Jeremy within the office. I answer to both. I've been with Gamma Technologies for 24 years. I'm the team lead of the engine and reactive flow systems application team at Gamma Technologies, looking over combustion, fuel cells, engine performance, acoustics, and even after treatment to some degree. And so hopefully that's a good enough intro.
Yeah, thank you, and congratulations on an upcoming anniversary as well.
Oh, thanks.
And if people are interested, they should also check out Lalit's LinkedIn. He makes some really interesting posts, so be sure to check that out. And I think we can get started on the topic. It's a very interesting topic, especially in the current climate of sustainability and all other initiatives going on. So could you talk about what exactly are net zero carbon fuels? What are we looking at, and why that's become significant in the current world?
I'll take it. Net zero carbon fuels, as the name implies, the goal is to provide a fuel that doesn't add more carbon dioxide to the atmosphere. So these can include fuels that have no carbon in them whatsoever, like ammonia and hydrogen, but also fuels that have carbon in them that the carbon came from the atmosphere originally. So biofuels count, where the plant life takes the carbon dioxide, converts it to the sugars, the oils, that are then converted into biodiesel or ethanol or something. Or there are carbon capture technologies that will capture that CO2 and then use it in the formation of a specific fuel. There's several types, but the ultimate goal is to not add more carbon dioxide to the atmosphere through these fuels.
Yeah, and to add to that, we have two types of this net zero carbon fuels. One is without any carbon atoms, as Jeremy mentioned, hydrogen, ammonia. There are some fuels which have carbon, so that carbon is coming from atmosphere, and they are classified into two parts. One is biofuels and one is synthetic fuels. The synthetic fuels are also called electrofuels. So these two types of fuels with other fuels are becoming popular to decarbonize difficult to decarbonize sectors of transportation, such as shipping industry, aviation, long haul, trucking. So all these sectors which are difficult to electrify, these industries are looking at these alternate zero carbon or low carbon fuels as a pathway towards decarbonization.
Thanks for the great introduction on the topic of net zero carbon fuels. I think the follow-up question probably for me is going to be, what are the challenges associated with adopting these kinds of fuels, whether they be carbon-free, synthetic or biofuels, and why now? Why are these gaining more and more importance now and not, let's say, 20 years ago? Is it policy? Is it just the challenges with the how they perform in engines? I would like your views on these.
I'll start. As we probably all of us know, there is a big goal and push to fully electrify, to go to battery electric vehicles. But the energy density of batteries at this time are not quite good enough for all of the individual applications, and probably the most significant application would even be aerospace, where weight is so important. If you look at the relative energy density of typical fuels, gasoline and diesel, which are hydrocarbons, it's like several orders of magnitude greater than the typical battery. Now, this is sufficient for a lot of passenger cars with short-term hauls and so on, but when you're getting into marine transport and locomotives, it's not as simple to do, and also the high cost of batteries at the same time relative to an IC engine has caused us to retain interest in using some kind of fuel, such as hydrogen, ammonia, whatever. And so that, in my opinion, that's the reason why there's still continued interest in IC engines. Yeah.
To add to that, right now 80% of the primary energy is coming from combustion, and even in a net zero scenario in 2050, it is projected that around 50% of the primary energy will come from combustion. And if you want to reduce the amount of CO2 in the atmosphere, then we have either two pathways. Either we stop combusting fossil fuels, or we replace these fossil fuels with net zero carbon fuels in order to meet that 50% primary energy coming from combustion. So that's why there's a renewed interest in these zero carbon or net zero carbon fuels for all of these applications, including transportation.
It's also nice that we can use our existing infrastructure, existing design, rather than completely pivoting to something else for a new technology. It's a lot easier on the adoption side itself. So yeah, certainly an exciting thing to look into, both research and also on the industry side. Is there are there a few things also stopping or some cons that the industry see in implementing it in terms of the initial investments or other challenges? Also, are there any differences in design that they have to explore in implementing or even starting to use some of these fuels?
Definitely. There are challenges. In some ways, it shows that fossil fuels, I don't want to call them a miracle fuel, but there's so many simple things about the hydrocarbon. The fact that they're liquid at room temperature, that they have a high energy density, they're relatively safe. You don't have to use special equipment to fuel up your tank and so on. Whereas hydrogen has problems in terms of leaking, so that tanks have to be designed specially. Now, the energy density on a mass basis is excellent for hydrogen, but on a volume basis, it's really bad. And so they need to be pressurized into these high pressure tanks, and some people are even looking at cryogenically storing them as liquids, which adds more expense, of course, but they're often stored in these tanks at 700 atmospheres or 700 bar in order to contain enough energy to get a reasonable trip out of it. So there is no simple drop-in solution in that respect. For hydrogen, for example, ammonia is poisonous and needs extra safety. Same thing with methanol. Methanol is highly dangerous, so that's not going to be as simple. It's better suited for industrial applications, maybe marine, where you can have specialized technicians do the refueling and make sure they do everything right to keep things safe. But there are many challenges that will have to be built up. Even the infrastructure needs more building for the higher pressures, the fact that hydrogen leaks through every little crack you can find.
It's the smallest molecule there is.
Exactly. And it's really good at finding a crack and slipping out. In fact, BMW, 20 years ago, BMW had been working on a hydrogen-powered IC engine vehicle. I think it was only a concept stage or experimental within their R&D department. But they reported that if you fill up the tank, and it was liquid hydrogen that they were using, but if you fill it up and don't let the car, don't use it for a week, eventually all that, it's going to leak during that time. So it's not something where you want to fill it up and let it sit around for a long time. So there's going to be challenges. It's going to, all of these fuels are going to give some challenges that will keep engineers employed as we look at this future.
And doesn't harm GT because we can model and simulate these in any scenario you can think of.
Yes, we build the tools to simulate, and so we're just staying caught up with what these technologies are, make sure we can simulate them, and then people can then study which ones might work best for their application and scenario and even regional difference.
And the low volumetric density for these fuels that you mentioned, it also has considerations in the range, like for the same fuel tank and the same efficiency, the half energy density leads to half the range as compared to fossil, like gasoline or diesel. So in terms of the vehicle design, these considerations needs to be taken basically for range, refueling frequency, all these things comes into picture.
So just a curiosity question for my sake, the current fuel tanks that are present in, let's say, a ship or a plane or a long haul truck, these cannot be repurposed directly with hydrogen or ammonia for burning right now.
No, for ammonia you can use the same, like in terms of material consideration there's a different aspect, and in terms of the range and the volume of the fuel that you need there's a different consideration. So for material you need a different coating of the fuel tank because these are toxic and reactive substances, ammonia and methanol. They do not behave similar to like diesel or gasoline. And from the range perspective, you need bigger volume of the tank to have the same range. So these are the things to consider.
Yeah.
So
Even Lalit, maybe you know this better than I do. Ammonia, I believe, is a gas at room temperature and pressure, and so it needs to be pressurized or cooled
Yes.
in order to store it as a liquid to get that high
So
energy
that too,
density,
yeah.
volumetric density.
There are two ways to do it. Either you cool it down a little bit, so at minus 33 degrees Celsius it becomes liquid, or you pressurize a little bit, so at 8 bar and room temperature it becomes liquid. So that's why it is being considered as a liquid fuel, because you just need a nominal pressure to liquefy it. And methanol is the simplest alcohol which is liquid at room temperature.
Yeah.
So any concerns with NOx emissions? Because I know you have got rid of the CO2 emissions, but now ammonia has nitrogen in it, so, and you are combusting, so the NO is probably the byproduct that is going to come out.
Yes. So NOx is the biggest challenge for ammonia combustion, apart from its combustion characteristics. For hydrogen as well, NOx is a big challenge because the adiabatic flame temperature of hydrogen is very high, and NOx is...
What's an adiabatic flame temperature?
So the maximum temperature that you get when you burn the fuel in a closed adiabatic or insulated system, the maximum temperature that you get is adiabatic flame temperature. And the NOx is directly proportional to the temperature of the flame or the system. So with these high temperatures in the combustion systems, you will get a lot of NOx. So that is especially true for ammonia and hydrogen. That's not true for methanol. Methanol has very high heat of latent heat, so it basically takes in a lot of heat and cools down the whole system. So it decreases the flame or combustion temperature. So NOx is less of a concern for ammonia, but it's a significant challenge for hydrogen and ammonia.
NOx
For
methanol.
For methanol, yeah.
And a phrase I had to learn about relating to ammonia combustion is they call it a fuel NOx. the fact that it, as you mentioned, it's in the fuel, it's right there where the reaction is occurring, and so the oxygen is breaking apart and recombining with the hydrogen to make water, but some of those will combine with the nitrogen to create NOx, more so than if there was no nitrogen in the fuel. So assuming that's what you were alluding to
Sure.
Earlier, and so that's another consideration. Another thing with hydrogen that I had to learn about was that we have to run at much lower relative fuel-air ratios. Hydrocarbons tend to produce the most NOx near stoichiometric, which is the ideal blend of fuel and air. To burn all of the fuel and not have any excess air. And so traditionally, at least in gasoline engines, most of the time it runs near that point. It does produce a lot of NOx, but that also helps the three-way catalyst run. For some reason I don't fully understand, maybe Lalit's studied this more. More NOx is produced at these lean conditions, and so one has to run much leaner than usual to start to bring the NOx formation down within the cylinder, which adds some challenges on air breathing and power density of the engine. So there are some unexpected challenges that are arising with hydrogen and some of these fuels that we'll pay attention to and continue to learn about.
I think we can take a little bit of a step back and move from the challenges. There are also a lot of positives to using these fuels, and that's what we were here in the podcast to talk about. So can you both highlight some of the things we can look forward to in these applications?
Wow. I mean, I guess I think the number one positive is the net zero carbon, the fact that we are meeting the goals of reducing the carbon dioxide in the atmosphere. There's the cost of the engine is much lower, just because it's a more established technology. And one interesting comparison, we've talked about hydrogen, and fuel cells are one option that are being considered for hydrogen as well. There was an interesting report from a company, JCB, that makes construction equipment, and they actually looked at making an excavator with both a fuel cell and an IC engine. And at least in the report, which, it's a couple of years old now, they said that the cost of a fuel cell excavator was over 300,000 pounds, and the equivalent IC engine with hydrogen fuel was 170,000 pounds. So, and I didn't get a breakdown of what those costs were. My best guess is the catalytic material needed by the fuel cell. It does need platinum or some other metal that to provide the catalytic reaction. And so that's probably the reason for it, but JCB is going forward with developing hydrogen for their engines, and many other manufacturers are doing the same. And there have been reports, Cummins, Deutz, either they have an engine ready to go or they've redesigned it, or they will have one ready for production by the end of 2024. Like Deutz, I believe I read in a little newsletter yesterday, is planning for 2024 Q4. So the technology is so much readily available, and there's there are modifications required for hydrogen, but not a lot, it appears.
Yeah, the development curve is a lot lower.
Yeah.
And
in addition to the cost, in fuel cell you need a very high purity hydrogen, but you can burn impure hydrogen in a combustion engine, so that's another advantage. And talking about advantages, these net zero carbon fuels reduces the amount of sulfur dioxide emissions and the particulate matter, which we typically call soot emissions. So that improve the air quality significantly if we use these fuels as compared to the traditional fossil fuels.
so you're saying we can get rid of smog and
Yes.
in India, China, and any other place where we have these things if we
Yeah.
adopt the fuels we are talking about today.
Yes, and they act as a drop-in fuel as well, so they'll be easy to implement in developing economies where we don't have infrastructure and cost benefits for electrification.
Yeah. It may depend upon the exact fuel, like the hydrogen and ammonia, since there's no carbon in the fuel itself, you bypass carbon monoxide completely. And I believe that's one of the major causes of smog, is
Yeah.
the carbon monoxide. So you can even lower the cost on your catalytic converter. You'll just need one to handle, okay, you'll need something for the NOx, and it's not a catalytic converter in the traditional sense, but they have variations of those devices to handle just the NOx, lean NOx traps and other devices.
If we can look at the regional considerations as well, like these fuels are being seen as fuels for energy security of the countries like Japan, where they don't have renewable power capacity. So they are looking at ammonia and hydrogen as a fuel for powering their economy. So there's another advantage of these fuels, that it decouples them from being dependent on these fossil fuel providers.
Yeah, arguably, as long as you have a clean electricity source, an electrolyzer, and a clean water source, anybody can produce hydrogen anywhere. And there's something, it's called the Haber-Bosch process that can create, that's ammonia, right?
Ammonia, yes.
There's another process for methane, but and that the nitrogen just comes from the atmosphere. So you can produce your own ammonia and hydrogen anywhere as long as you have clean sources of electricity. So and that actually leads into some other interesting points that we may get to later.
Speaking of what everybody can produce, everybody needs to consider a lot of conditions designing this too, and that's when we come in as a simulation software tool in GT.
Right.
And I think we have a whole suite of features that we do to support many of the both the challenges and the positives that you both talked about. Could you highlight some of the things that we can offer from a modeling and simulation perspective that can make this whole design process and implementation process easier?
Well, I'll give first guess on that, or first try at that. So the IC engine is, or modeling of the IC engine has been the strong suit of GT Power and GT Suite for, we're approaching 30 years now. Of course, we've expanded from that. And GT Suite is always the developers, the founders and the developers in the continuing time, have always tried to work from a fundamental approach using a modular design approach, so that it's surprising how flexible the code can be, where some potential users will wonder, can GT handle this or that? And in the past few years, it's been hydrogen. Can GT handle hydrogen? I know you've done well with gasoline and diesel, but in more than 20 years ago, we were developing, making sure that we could burn hydrogen, because we knew there were companies like BMW who were researching it, and we wanted to make sure our code was capable of doing that. So more than 20 years ago, we were able to handle hydrogen, and I think nitrogen was possible just because of that same development. The problem was, is there carbon or is there not carbon? And so once we solved the no carbon problem for hydrogen, ammonia sort of took place. Now that's basic burn rates. We use equilibrium chemistry, which is kind of a quasi-static approach for chemistry in the cylinder. It's faster than trying to do full kinetics, but in doing so, we can burn release the heat, produce the power, make that prediction. The second level of combustion is predictive combustion. So it's predicting the burn rate based on the conditions in the cylinder, the shape of the piston, the head, the location of the spark, and how much pressure there is, what's the compression ratio, and so on. And so the one key has been what's called the laminar flame speed. This is the speed at which the flame burns through a quiescent or a still mixture of fuel and air. And so we've had fuels for gasoline, ethanol, and so on for a long time. We've had hydrogen for almost 20 years, more than 20 years now. And so that's one of the challenges. We're finding little challenges along the way, like fuel stratification when it's injected directly has been something we've learned about in the past few years, and we've added a development, and we're monitoring how well it's working, and we're willing to work on more as we learn more information about it. But for the most part, if someone were to ask me the simple question, can GT Suite model hydrogen and ammonia, my quick answer is yes. We can go into individual details, but that's the broad picture, and we're always trying to refine the model further.
And in recent years, we have added detailed chemistry solvers, so where we can use the detailed reaction mechanisms for these fuels to predict emissions, and also we know how individual fuels burn, like ammonia on its own or hydrogen on its own, but people are trying to blend these fuels in different proportions and trying to see if they can make it work by improving the combustion properties. So predicting their proper combustion characteristics of these blends is another challenge, where we have detailed chemistry solvers which can help our customers in simulating or generating data for these different blend levels. So that's another area that we have focused a lot in recent years and developed very fast chemistry solvers for very large reaction mechanisms.
Yeah, that's a great point. For example, ammonia has relative to the other fuels, burns very slowly. And so one of the things people are looking at, or one of the options, is mixing a little bit of hydrogen in order to speed it up, because hydrogen is actually faster than gasoline and most of the other fuels, fortunately. And so by adding some, you can bring the overall average back to a normal level, if you want to call it that, but a more typical level. And so that's an avenue of research our customers are looking at in the future. And GT does have tools to help one predict the laminar flame speed from the chemistry, as long as you have the some kind of chemical mechanism. And we're keeping our ears to the ground, so to speak, on what those mechanisms are, and providing them when we can to our customers.
And there was an interesting study I came across where, so in case of this ethanol and methanol, when they're produced, they have water content in it. So they first remove the water to produce this anhydrous methanol. But if we can eliminate that step, and if we can use the hydrous methanol, which is basically a mixture of methanol and water or ethanol and water directly, then we can save on the cost for dehydrating the original methanol. So how does that mixture of water and ethanol burn in an engine? We can tackle those questions as well using our simulation tools by looking at their flame speed, burning speed, ignition delay of these fuel mixtures in presence of water, and also how does the presence of water affect the emissions. For example, it reduces NOx by lowering the temperature. So these are the challenges that we can easily simulate using the GT Suite software.
And I think to add to that, not just in cylinder, I have seen our customers use it for even doing filling station simulations as well. So any infrastructure that is going to be associated with the new fuel economy that we are going into, I've seen people use it all the way from the filling tank to the final air capture that they probably are doing on a vehicle as well. I don't think there is an application where I've seen them not being able to use GT Suite, all the way from thermal management to pumps, compressors, engines, and I think our software and developers, R&D teams are aligned well enough that we can get everything working together, because I think this is a endeavor where all these systems need to come together. If we only know what is happening inside the cylinder, we might be limited in what kind of studies we are able to do as well.
Basically, where system simulation becomes really
Yes,
powerful,
exactly.
yeah,
Yeah.
between different systems.
And to add to that system simulation, recently we added fuel reforming examples in after treatment.
Yes.
So a lot of I have seen a few studies where these fuel reformers are used in conjunction with IC engine. So for example, when you use ammonia, you use a fuel reformer which basically cracks the ammonia into a little bit of hydrogen and ammonia, so it improves the combustion properties. So before sending the ammonia directly into engine, you reform it a little bit to produce hydrogen, and then send that mixture to the engine to improve the combustion characteristic. Similar thing you can do with methanol, because methanol also has poor combustion characteristics. So you reform methanol a little bit to produce syngas. So it is a mixture of CO and H2 with methanol, and then send that mixture into IC engine to improve the combustion properties. So these reformers along with IC engines makes a very good system level simulation study where we can come into simulating this.
Can we also replace the IC engine with a fuel cell and do the same kind of study in a similar system model with hydrogen being the input?
Yes, I believe that has also been done where ammonia is used as a hydrogen carrier rather than as a fuel, and then that hydrogen is sent to fuel cell for modeling that fuel as a fuel basically.
It doesn't use hydrogen, but at our recent conference, I believe in the U.S., one of our presenters did a study of hydrogen engine and fuel cell.
Wow.
I need to double check the exact thing, but it was, we could maybe look it up and.
Just to point out to our viewers, this is
Yeah.
talking about the GT user conference in 2023.
Yeah.
I think we've had a pretty productive discussion, and it seems to be a very exciting time for net zero carbon fuels.
Mhm.
And I think as engineers, researchers, exciting times are the most interesting.
Yeah.
Because you get to work on all the challenges.
Right.
Once a technology gets established, there is not a lot to do. So
Right.
these are, I think, the most exciting
But
times.
apparently we were thinking of hydrogen 20 years ago. So,
So we've been at the cutting edge.
yeah,
since
we'll be
20
thinking of the
years
next
ago.
20 years too.
Exactly.
And I hope we can be as predictive of future technology as we used to be
Yeah.
previously. Thanks again, Lalit and Jeremy, for joining us. It was great talking to you, and I've certainly learned so much about net zero carbon fuels.
Yeah, same here. And thanks for joining us.
All right. Thank you for inviting us.
Thank you for hosting us. It was a great discussion.
Yeah.
Yeah, thank you.